And now in this lecture we find out the area of the small circle. In the drawing we have a big semicircle. We know that line segment AQ equals to 2 units in its length, line segment TB equals to 8 units in its length. This is angle PQA, that is a right angle, and this is angle STB, that is also a right angle. Inside this big semicircle, we have this small circle, and our mission is to find out the area of this small circle. So first of all, we will define the relevant points to this question with letters. We will define the center of this big semicircle. This point is point H. We will define the center of this small circle. This point is point K. We will define the point of tendency of tangent AB with this small circle. This point is point M. We will define the point of tendency of tangent ST with this small circle. This point is point L. We will define the point of tendency of tangent PQ with this small circle. This point is point T. In the next step, here we can actually implement all three. According to all three, the sum of the angles on one side of a straight line is equal to 180 degrees. AB is the diameter of this big semicircle. AB is a diameter, it is absolutely straight lines. So if you focus on the upper side of this straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to all three. In this case, it means that the sum of the angles of the upper side of AB at point Q must be equal to 180 degrees according to all three. So which angles we have at the upper side of AB at point Q? We have this angle, that is the right angle, plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. We continue to focus on the upper side of the straight line AB at point T. Here the sum of the angles must be also equal to 180 degrees according to the sum rule, all three. So which angles we have at the upper side of the straight line AB at point T? We have this angle, that is the right angle, plus the size of this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points K and M together by a straight line. What is the definition of the straight line KM? The straight line KM starts from point K, that is the center of this small circle, and ends at point M, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, Km is the radius of this small circle. We define the radius of this small circle as x, therefore Km equals to x. Here we can implement all 1. If it's quicker on all 1, according to all 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have tangent AB, that is tangent to this circle, to this point, point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that equals to R. the radius OM is drawn to point M, that is the point of tendency of tangent AB with this small circle. Whenever a radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius Km, that is equals to x. The radius Km is drawn to point M, that is the point of tendency of tangent AB with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points K and T together by a straight line. KT is the radius of this small circle, that is equals to x according to our definition. Again, we have the radius KT that is drawn to point T, that is the point of tendency of tangent PT with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius TK. If PK is perpendicular to TK, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will focus on the small quadrangle TKMQ. Inside the small quadrangle TKMQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrangle TKMQ, we have 4 right angles. And according to rule 6, any quadrangle that has 4 right angles must be this rectangle if not a square. So we relate to this small quadrangle TKMQ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle TKMQ, side TK must be equal to the opposite side MQ. But TK is x, therefore MQ must be also equal to x. Likewise, according to the same rule, in the same rectangle TKMQ, side KM must be equal to the opposite side TQ, but KM is x, therefore TQ must be also equal to x. So actually found out that the small quadrangle TKMQ is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Its side equals to x. So I have to know this quadrangle TKQM is a square. In the next step, we join points K and M together by a straight line. KL is the radius of this small circle, is equal to x according to our definition. Here, the radius KL is drawn to point L, that is the point of tendency of tangent ST with this small circle. Whenever radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LK. If ST is perpendicular to LK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside the small quadrangle KLTM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside this one quadrangle KLTM, we have 4 right angles. And according to rule 6, any quadrangle that has 4 right angles must be this rectangle if not a square. So we relate to this quadrangle KLTM, it's a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle KLTM, side KL must be equal to the opposite side MT. But KL is x, therefore MT must be also equal to x. Likewise, according to the sum rule, in the sum rectangle KLTM, side KM must be equal to the opposite side LT. But KM is x, therefore LT must be also equal to x. So actually found out that the small quadrangle around KLTM is not a rectangle but a square, because all three sides are equal to each other, its side equals to x. So I write it down. What is the size of angle LKT? The size of angle LKT is equals to 90 degrees plus 90 degrees, that is 180 degrees. And we know that any angle that is equals to 180 degrees in size is defined as a straight line. Therefore, angle LKT is a straight line. Angle LKT is a straight line. So line segment LKT is a straight line. If line segment LKT is a straight line, it means that LT is also a straight line. So LT is a straight line, but LT is a straight line that touches the circle 2 points, L and T. And we know that any straight line that touches the circle 2 points, it is defined as a chord. So LT is a chord, LT is a chord that passes through point K, that is the center of this small circle, and we know that any chord that passes through the center of the circle must be the diameter. Therefore, LT is the diameter of this small circle. So I write it now. Actually found out that LT is the diameter of the small circle. LT is the diameter of the small circle. Anyway, LT, of course, it is a straight line. And because of the fact that LT is a straight line, it means that shape TL, TQ is a quadrangle. So here we have 2 points with the same letter. So I change the definition of this point. Instead of point T, we write down that is point N. Okay, so this is point N. We know that NL is a straight line, therefore shape NLTQ, this shape NLTQ is a quadrangle because it has 4 sides, 1, 2, 3, 4. So inside quadrangle NLTQ, we have 4 right angles, 1, 2, 3, 4. And we know that according to rule 6, any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrangle NLTQ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NLTQ, side NL must be equal to the opposite side TQ. But NL is the diameter of the circle. It is equal to x plus x, that is 2x. Therefore, TQ must be also equal to 2x. According to the rule, the opposite sides of a rectangle are equal to each other. So, TQ equals to 2x units in its length. what is the radius of the big semicircle? We define the radius of this big semicircle is capital R. What is the value of capital R? That is the radius of the semicircle according to our definition. The value of capital R must be equal to the diameter of this semicircle over 2. AB is the diameter, so the diameter AB over 2 must be equal to the radius of this semicircle, that is capital R. So the radius of the big semicircle capital R equals to the diameter AB over 2. But what is the length of the diameter AB of the semicircle? AB, in total AB equals to 2 plus 8, that is 10, plus 2x. Again, 10 plus 2x is the length of the diameter AB. So I write it down. The length of the diameter AB is 10 plus 2x, and if we divide the diameter AB by 2, we get the radius capital R of the semicircle. So the radius capital R of the semicircle equals to 10 plus 2x over 2. 10 over 2 is 5, 2x over 2 is x. So in total, we actually found out that the radius of the big semicircle capital R equals to x plus 5 units in its length. Okay. Repeat again. The radius of this big semicircle, capital R, equals to x plus 5 units in its length. Okay. Here we can implement rule 9. Why? Because we have an internal notch between this small circle and the big semicircle. That is to say, they are touching each other internally at this point. Whenever we have an internal notch between two circles, you can implement rule 9. So, I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. In the drawing, we have two circles, and they touch each other internally at point P. Point P is their touching point. The center of this big circle is 0 at point O. The center of this small circle is 0 at point M. And the straight line that connects their centers together is, of course, the straight line OM. So this straight line OM must pass through point P, that is their touching point. The straight line OM must pass through point P, that is their touching point, or OMP is one straight line. Again, OMP is one straight line, according to this rule, rule 9. We can actually implement rule 9 in our drawing, because we have an internal notch between this small circle and the big semicircle. That is to say, they are touching each other internally at this point. Therefore, we can implement it rule 9. The center of the big semicircle is at point H, and the center of this small circle is at point K. And the straight line that connects the centers together is, of course, the straight line HK. And according to rule 9, the straight line HK must pass for this point, that is their touching point. Okay, so I connect points H and K together by straight line, and according to rule 9, the straight line HK must pass through this point, that is their touching point. You can see from the drawing that indeed the straight line HK passes through their touching point. This is their touching point. We define the touching point of this small circle, the big semicircle, this point is point D. You can see from the moment that the straight line HK passes through point D. Again, the straight line HK passes through point D, or HKD is one straight line. Again, HKD is one straight line. If HKD is one straight line, it means that HD is also a straight line. Again, HD must be also a straight line because HKD is a straight line. HD is a straight line. But what is exactly the definition of the straight line HD? The straight line HD starts from point H, that is the center of the big semicircle, and H at point D, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, HD is the radius of this big semicircle, and we already found out that the radius of this of the big semicircle, capital R, equals to x plus 5. So we can write down actually that HD equals to x plus 5, it is the radius of the big semicircle. What is the definition of line 7 KD? Line 7 KD starts from point K, that is the center of the small circle, and that's at point D, that is the point of the small circle itself. Therefore, KD is the radius of this small circle, that is equal to x according to our definition. KD equals to x. What is the value of the missing side KH? From the drawing, it is very easy to see that KH in total equals to DH minus DK. Again, DH minus DK equals to KH. So KH equals to DH, that is the radius of the big semicircle, minus DK, that is the radius of the small circle. So in total, I can find out that this missing side KH, the missing side KH equals to DH minus DK. DH or HD, so KH equals to DH. DH or HD, it is the same. It is the radius of the big semicircle that equals to x plus 5 minus DK. DK equals to x. So in total, the missing side KH equals to x plus 5 minus x. X minus x is 0, and we left only with 5. So I actually found out that the missing side KH equals to 5 units in its length. Here, the missing side KH equals to 5 units in its length. What is the length of the missing side MH? From the drawing, it is very easy to see that MH in total equals to AH. AH is the radius of the big semicircle. It is AH minus AQ minus QM. Again, AH minus AQ minus QM equals to the missing side MH. So the missing side MH equals to AH, that is the radius of the semicircle, minus AQ. EQ equals to 2 minus QM. Minus QM, that is equals to x. So MH in total equals to AH. AH is the radius of the semicircle, that is equals to capital R, and capital R equals to x plus 5. the radius of the semicircle equals to x plus 5 minus AQ. AQ equals to 2 minus QM. QM equals to x. So today I actually found out that the missing side MH equals to x plus 5 minus 2 minus x. So here x minus x is 0. So x will get cancelled. And 5 minus 2 is 3. So today I actually found out that the missing side MH equals to 3 units in its length. This is the missing side MH. That is equals to 3 units in its length. In the next step, I'll copy the right green triangle, triangle KMH. This green one, triangle KMH in the new page. And we will implement the Pythagoras theorem in this right green triangle, triangle KMH. Here by PT is the equation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side Km of the green triangle equals to x. This is the radius of the small circle. We just right now found out that the missing side MH equals to 3 and the hypotenuse KH equals to 5. So actually, this is the right green triangle, triangle KMH that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle KMH, KH squared, that is the square of the hypotenuse, must be equal to KM squared plus MH squared. Again, KH squared equals to KM squared plus MH squared. So I write it now. KH squared, the square of the hypotenuse, equals to KM squared plus MH squared. KH, the hypotenuse KH is 5, therefore KH squared is 5 squared, that is 25. And it is equals to KM squared. KM is x, therefore KM squared is x squared plus MH squared. MH is 3, therefore MH squared is 3 squared, that is 9. The conclusion we found out that according to the Pythagoras theorem, 25 equals to x squared plus 9. Here we subtract 9 from this equation, and finally we get that x squared equals to 25 minus 9 is 16. So x squared equals to 16 units. Here we take out of this equation. We take out of this equation and we get that x equals to the square root of 16, that is 4. So we found out that the radius of this small circle, x equals to 4 units in its length. Our mission is to find out the area of this small circle. And we know that the area of any circle equals to pi times the radius of the circle squared. So the area of this small circle must be equal to pi times the radius of the circle squared. The radius of this circle is x, therefore the radius squared is x squared. So the area of our circle equals to pi x squared. So it is pi, and we already found out that x squared equals to 16, so substitute x squared by 16. So I actually found out that the area of this small circle, that is the area that we are looking for in this question, equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Repeat again, I actually found out that the area of this small circle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Okay, so in the next step, I'll summarize the lecture. Our mission, this question is to find out the area of this small circle. So in the drawing, we have a big semicircle. We know that line segment AQ equals to 2 units in its length. Line segment TB equals to 8 units in its length. This is the angle NQA, that is a right angle. This is the angle STB, that is also a right angle. I repeat again, our mission is to find out the area of this small circle. So first of all, we defined the relevant points to this question with letters. We defined the center of the big semicircle, this point as H. We defined the center of this small circle, this point as point K. We defined the point of tendency of tangent PQ with this small circle, this point as point N. We defined the point of tendency of tangent ST with this small circle, this point as point L. We defined the point of tendency of tangent AB with this small circle, this point as point M. We finally defined the touching point of the big semicircle with this small circle, this point as point D. In the next step, we implemented in our drawing all three. I'll repeat quickly on all three. According to all three, the sum of the angles on one side of a straight line is equal to 180 degrees. AB is the diameter of this semicircle. So AB is the diameter, it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to all three. So which angles we have at the upper side of AB at point Q? We have this angle, that is the right angle, according to what is given in the question, plus this missing angle. In total, they must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we continue to focus on the upper side of the straight line AB at point T. So, we know that at the upper side of AB at point T, the sum of the angles must be equal to 180 degrees according to all three. So, which angles we have at the upper side of AB at point T? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size according to all three. In the next step, we join points K and M together by a straight line. What is the definition of line segment KM? Line segment KM starts from point K, that is the center of this small circle, and that's at point M, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, Km is the radius of this small circle. We define the radius of this small circle as x. Therefore, we define the radius of this small circle as x. Therefore, Km equals to x. Here we can implement rule 1. Because we have the radius Km of this small circle. The radius Km is going to point M. That is the point of tendency of tangent AB with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points K and N together by a straight line. Kn is the radius of this small circle. That is equals to x according to our definition. The radius Kn is going to point N, that is the point of tendency of tangent PQ with this small circle. And whenever we have a radius that is 1 to the point of tendency, then tangent PQ will be perpendicular to the radius NK. That is to say, this angle must be equal to 90 degrees, and this angle must be also equal to 90 degrees. By doing these constructions, we actually created here quadrangle K and QM. Inside quadrangle K and QM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrangle KN QM, we have 4 right angles, and according to rule 6, any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we relate to this small quadrangle KN QM, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So an rectangle KN QM, side KN must be equal to the opposite side QM, but KN is x, therefore QM must be also equal to x. Likewise, according to the same rule, in the side of the KN QM, side KM must be equal to the opposite side NQ, but KM is x, therefore NQ must be also equal to x. So we actually found out that quadrangle KN QM is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square equals to x. Likewise, we repeated on the same process on quadrangle KN TM. Inside quadrangle KN TM, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees in its size, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. 60 degrees. So quadrangle KLTM is 4 right angles, therefore we can relate to this quadrangle KLTM as a rectangle according to rule 6. So in rectangle KLTM, side KL must be equal to the opposite side TM. But KL is x, therefore the m must be also equal to x. Likewise, according to the same rule, in the same rectangle KLTM, side LT must be equal to the opposite side KM. But KM is x, therefore LT must be also equal to x. So we actually found out that quadrangle KLTM is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side equals to x. So quadrangle KLTM is a square. So what is the length? What is the size of angle NKL? The length of side NKL, again, the length of angle NKL, this is angle NKL, and the size of angle NKL equals to 90 degrees plus 90 degrees, it is 180 degrees. So angle NKL equals to 180 degrees in its size, and we know that any angle that equals to 180 degrees in its size, it is defined as a straight line. Therefore, angle NKL equals to, it is a straight line, angle NKL is a straight line. So, line segment NKL is a straight line, therefore, NL is also a straight line. NL is a straight line that touches the circle at 2 points, N and L. And we know that any straight line that touches the circle at 2 points, it is defined as a chord. So, NL is a chord. But NL is a chord that passes through point K, that is the center of the circle, and we know that any chord that passes through the center of the circle, it is defined as the diameter of the circle. Therefore, NL is the diameter of this small circle. So I'm repeating again. N or N is the same, is the diameter of the small circle. So in the next step, we found out the radius of the big semicircle. The radius of the big semicircle, first of all, we define the radius of this big semicircle as capital R. So capital R will be equal to the diameter AB over 2. Again, AB is the diameter of the semicircle, so the diameter over 2 must be equal to the radius. So capital R, that is the radius of the semicircle according to our definition, must be equal to AB, that is the diameter of the semicircle, over 2. Okay. But here, first of all, before we find out the radius of this big semicircle, we actually know that NL is the diameter of the small circle, therefore it is absolutely a straight line. So shape NLTQ is a quadrilateral because it has four sides: 1, 2, 3, and 4. So shape NLTQ is a quadrilateral. Inside quadrilateral NLTQ we have 1, 2, 3, 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we write to quadrilateral NLTQ as a rectangle because of the fact that it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NLTQ, side NL must be equal to the opposite side TQ. But NL is the diameter of this small circle that equals to 2x. Therefore QT must be also equal to 2x. Okay, so if we know that QT equals to 2x, now we find out the radius of this big semicircle. We define the radius of this big semicircle as capital R. The radius of this big semicircle must be equal to the diameter AB over 2. So repeat again. The radius of the big semicircle is equal to capital R according to our definition must be equal to the diameter AB over 2. But what is the length of the diameter AB? The length of the diameter AB is 2 plus 8 plus 2x. Again, the diameter AB in total equals to 2 plus 8 plus 2x. So the diameter AB equals to 2 plus 8, that is 10 plus 2x. And again, the diameter AB in total equals to 10 plus 2x. And the diameter over 2 is the radius of the capital R. So AB over 2 is 10 plus 2x over 2. 10 over 2 is 5 and 2x over 2 is x. So total, actually found out that the radius of the big semicircle capital R equals to x plus 5. But again, the radius of this big semicircle equals to x plus 5 units in its length. So here we can implement rule 9 because we have an internal notch between this small circle and the big semicircle. That is to say they are touching each other internally in this point D. Whenever we have an internal notch between two circles, you can implement rule 9. I'll quick quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects the circles together passes through their touching point. So we have here two circles that touch each other internally is point P. The center of the big circle is at point O. The center of this small circle is at point M. And the straight line that connects the centers together is the straight line OM. And according to this rule 9, the straight line OM must pass for point P. That is their touching point. Or OMP is one straight line. Again, OMP is one straight line according to this rule 9. We can actually implement rule 9 in our drawing, because we have in our drawing internal notch between the big semicircle and the small circle at point D. The center of the big semicircle is here at point H. The center of this small circle is here at point K. And the straight line that connects the centers together is the straight line HK. And according to rule 9, the straight line HK must pass through the attaching point, that is point D. Or HKD is one straight line. If HKD is one straight line, it means that HD is also a straight line. But what is the definition of the straight line HD? The straight line HD starts from point H, that is the center of the semicircle, and ends at point D, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, HD is the radius of the big semicircle that is equal to x plus 5 units in its length. And again, HD is the radius of the big semicircle that is equal to x plus 5. According to what we have already found out, HD and the radius of the big semicircle is capital R, and it is equal to x plus 5. So 8D is the radius of the big semicircle, that is equal to x plus 5. What is the definition of line segment KD? Line segment KD starts from point K, that is the center of this small circle, and ends at point D, that is the point of the small circle itself. So this is exactly the definition of radius. Therefore, KD is the radius of this small circle, that is equal to x. So what is the length of the missing side edge K or KH? KH equals to DH minus DK. Again, DH minus DK equals to the missing side KH. Repeat again. The missing side KH equals to DH, that is the radius of the semicircle, minus KD, that is the radius of the small circle. So KH in total equals to DH, that is the radius of the semicircle, that is x plus 5, minus KH, that is the radius of the small circle, that is x. So in total KH equals to x plus 5 minus x. X minus x is 0, so we left with 5. In conclusion, we actually found out that this missing side KH equals to 5 units in its length. In the next step, we found out the length of the missing side MH. What is the length of the missing side MH? From the drawing, it is very easy to see that MH in total equals to AH, that is the radius of the semicircle, minus AQ minus QM. Again, AH minus AQ minus QM equals to the missing side MH. Repeat again, the missing side MH in total equals to AH, that is the radius of the semicircle, minus AQ, that is 2, minus QM, that is x. Here, QM is x. So in total, the missing side MH equals to AH, that is the radius of the semicircle, that is x plus 5, minus AQ, that is 2, minus QM, that is x. Again, AH is the radius of the semicircle, that is x plus 5. AQ is 2 and QM is x. So in total, the missing side MH equals to x plus 5 minus 2 minus x. X minus x is 0 and 5 minus 2 is 3. So in total, we found out that the missing side MH equals to 3 units in its length. In the next step, I copied this right green triangle KMH in a new page, and we implemented the Pythagoras theorem in this green right triangle KMH. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right green triangle KMH that I copied from the original domain. The hypotenuse KH equals to 5. KM is the missing side, it is the radius of the small circle. Km is the radius of the small circle, that is x. And we just now found out that MH equals to 3 units in its length. According to the Pythagoras theorem, in this right triangle KMH, KH square equals to KM square plus MH square. So KH square equals to MH square plus KH square equals to KM square plus MH square. So KH square, that is the square of the hypotenuse. KH is 5, therefore KH square is 5 square, that is 25. And it is equals to Km square. Km is x, therefore Km square is x square, plus Mh square. Ms is 3, therefore Ms square is 3 square, that is 9. So in total, according to the Pythagoras theorem, we actually found out that 25 equals to x square plus 9. If we subtract 9 from this equation, we finally found out that x square equals to 25 minus 9, that is 16. So x square, that is the square of the hypotenuse, x square, that is the radius of this small circle squared is 16. We took out of this equation, we found out that x, that is the radius of this small circle, x equals to the square root of 16, that is 4. So the radius of this small circle equals to 4 units in its length. Our mission is to find out the area of this small circle. And we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle equals to pi and the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, we actually found out the area of our circle, small circle, equals to pi x squared. But we already found out that x squared equals to 16, therefore we can substitute x squared by 16 in this equation. We did it and finally found out that the area of this small circle equals to either 16 pi square units, or in terms of numbers, the area of this small circle, that is the area that we are looking for in this question, equals to 50.265 square units. Okay? Thank you very much.